3 minutes in. So I'm going to start. If you all have any questions, you can feel free to put them in the chat. I'll monitor the chat, etc. But let's get started. My name is Sarah. I'm the curriculum manager for open learning at AI4ALL. And that means I write the curriculum. I also allow create PD sessions and that sort of thing, teacher support, that sort of thing. Also, I like to introduce myself as a human. I majored in computer science in high school, or in college, entirely because in high school, I was on the first robotics team. And I said, aha, that robot is only doing exactly what I'm telling it to, phenomenal cosmic power. So I always tell people I majored in phenomenal cosmic power. And I had a lot of fun doing so. And I wanted more people to get to have more fun. So I went from majoring in computer science to teaching. And that's how that happened. From there, I've taught at a couple of different schools, every grade between 2nd and 10th at some point. I helped write the curriculum for Girls Who Code. I also helped write the curriculum for Google CS First. And now I'm here. And also, unrelated to work, I love theater and cello. Not that everything is, you take your whole self, etc. I play cello. I love theater. I also love board games. That's sort of a quick introduction to me. I'm also going to give you a very quick introduction to AI4ALL, the org I work for. And then we're going to play with some activities. If you have the chance, and you could put into the chat what it is that, what your background is with computer science and AI, what you want to get out of this session. I'll try to sort of match what I'm saying and what we're doing to what you all are interested in. It is our mission at AI4ALL to increase diversity and inclusion in AI development, education, policy, and research. Why? Because there's a lot of AI in the world, and the people developing it do not match the people using it. So we want to encourage more people to be exposed and become the next leaders in moving AI in a positive direction. And of course, those are people making policy. Those are people making art. There's lots of ways that you can use AI to improve the world and to improve AI. We have a couple of different programs. We have high school curriculum for teachers in classrooms. That's what we're going to focus on. We also have high school curriculum for grad students and professors in colleges to teach high school students over the summer through a summer program. We also have college pathways for college students to be introduced to AI and hopefully want to follow from there. And all of these people wind up in Changemakers, which is our community for alums. We help them find networking and internships and such. But again, I'm going to mostly focus on open learning. It is our open learning philosophy that anyone can teach AI and that everyone has something to bring to teaching AI. This isn't like anyone can teach AI because AI is so easy. This is you as an English teacher already have a good understanding of how humans make meaning from words. And you can take that understanding to helping your students understand how computers make meaning from words. So it's my job to have a full-time job understanding curriculum. And it is your job to understand your students and the world that they're in, the ideas that they have, and the ideas that you have in your subject. We try to make it as easy for you as possible, but we also believe that you are bringing a lot to the classroom. This isn't a purely boxed, you can follow my script. There is a script. You can follow it if you want. But I view the curriculum I create as a toolbox for you to bring your excitement for your subject and your students to your classroom. So for some examples of this, all of our lessons have some critical thinking, some discussion, research processes, ethics, collaboration, and all of those things are things that you want in any subject. We have an AI day for schools that we're beginning to talk about. We haven't run it yet, but each class of the day has some kind of lesson and skills involved in AI. So it's just, when you go to science class, you'll do this AI lesson. When you go to ELA class, you'll do this AI lesson. Meant largely for the sorts of days where you have students who, like a couple of days before Thanksgiving or between the AP tests and the end of the year, a sort of fun theme day to learn things in. We have approximately 100 hours overall of curriculum. If you'd like to run all 100 hours, we have a scope for an order that I recommend running all 100 hours in. You definitely don't have to. We also have a 10-hour overview that if you just want to introduce AI in whatever class you are in, it gives you some of the like how AI gets used, etc. But yeah, so English teachers, they need to analyze articles. They need to discuss how humans and computers learn and find meanings in words and how they find sentiment. There's also the ethics curriculum. Social studies classes need to understand law and policy and civic participation. And we have a law and set of curricula about law and policy. Career and tech ed, needs to explore different career paths. We have all of our lessons end with examples of people in AI and how they got there. And if you're looking for the more technical curricula, we have some programming and we have how it works. We're going to mostly dive into how it works today because this is about all of the how we explain how things work without assuming that you have any particular math background. We also have AI in dance. Arts teachers can understand how to see AI as an artistic tool. We give you the content. We also provide some PD. Usually I run lessons for you, for instance. Everything's available for free online and should be accessible by individual educators. So that's enough about us. Let's quickly, so if y'all have access to the slides, it's on slide 10. Look at some examples. You can pick one, and I'll give you about a minute to play with some examples of AI. And also imaginary soundscape. I've also done this one, so. I'll give you about a minute. You can play with any of those, and then tell me sort of what you see in these. What are they doing? And as you learn what each of them are doing, what do they have in common? So you can put anything you're noticing in the chat, the questions I ask in particular, what did the activity play with do, how is it similar to the other activities? I'm going to have to keep moving along. So I'm not really going to wait for answers in the chat for the moment. But each of these activities involve the computer guessing things. So with the lip sync one, it has to guess where your lips are to find them to see if you're lip syncing correctly. For the soundscape, it makes a guess about, like, it sort of understands what the area you've described is and makes a guess about what it sounds like. I've typed in my own address here. It exactly sounds like my neighborhood. It's pretty cool. And the Wombo art, it's never made this art before, right? It's guessing what a picture would look like that it follows the description you've given. This leads us to AI4ALL's definition of AI, which is a discipline concerned with the designing of computers that make predictions. Remember, I said it was guessing what the places would be like, and decisions. But as you've played with different AI things, you might have come up with different answers. I'd also like to take a moment to describe machine learning. So here we have some pictures of some things that we're calling kalas, and here we have a picture of some things that we're calling batas. And then we have a shape down here. What is this shape? I made up these things, so you definitely didn't know coming in what this shape was. Anyone can type in the chat. What do you think this thing is? It could be a bird. In this particular case, we have exactly 2 words that I am thinking about. Stacy suggests that it's a kala. I agree. I think it's a kala. And why? Well, you see that the kalas have these like sharp edges, and the batas have these like rounded edges, and this has sharp edges. And we just got there from, here are some examples. And here's a new thing you've never seen before. Which of these examples is it more like? So that's basically what machine learning does. In machine learning, a computer takes in data, it's fed, and figures things out rather than being told by a programmer what something is necessarily. All machine learning is artificial intelligence. In any machine learning, the computer is making predictions and decisions. Not all AI is machine learning. Most AI that you talk about nowadays is going to be machine learning. So when we say AI is everywhere, we mean machine learning. Just quickly going into Deep Blue was a program that had every single possible move in chess laid out to it, and was also told, we expect this to be this good of a move for your opponent. You can imagine that your opponent's going to pick the best move from this list. You should pick the best move for you, assuming your opponent is going to pick the best move for them. So it's still making predictions. It's assuming that the player is going to make the thing that the programmers thought was the best move for it. But it didn't learn anything. AlphaGo, on the other hand, saw lots and lots of games of Go, and used the information it learned from lots and lots of games of Go to figure out its own way to win the game. So that's machine learning, which is also AI, whereas Deep Blue did not require any machine learning. Learning goals of every open learning thing. We want to figure out what AI and machine learning are, how it affects me and my community, benefits and drawbacks, and how we can affect it. We do that through lots of discussions, Google slide decks. There's also optional printable worksheets and Google Forms so students can fill things out online. We'll often give you videos, and anytime there's a video, I'm not going to actually show you this video, but anytime there's a video, there's also a question on the side so the students know why they're watching this video. There's also, which I don't have here, we also have a video overview in case you don't have time to watch the video, or in case you're a student that has an easier time understanding things that have been given to them in words rather than with a video. It's also just an extra place to summarize. So we often have videos, there's a bunch of research projects and presentations for the students to do. They also do a lot of what we did to begin here, like exploring some AI resources, playing with things. I very much want for students to feel like they are asking questions, and the class is answering questions that they have. So I try to open the class with things that will get students asking questions. And through each answer, I try to open up more questions, so that the students are sort of going on a journey of deeper and deeper understanding that they feel like that they should be motivated to keep going on. Every now and again, there'll be some group embodied learning. In Unit 4 of Explore AI, there's interviews. Very, very occasionally, there's programming, though, again, this is about the lessons that don't have programming. And AI and dance gives students the chance to choreograph their own dance using AI. These are sort of building blocks of all the curriculum. We try to help students take ownership of their own learning. We try to teach things multiple different ways, unlike what I'm doing right now, which is just talking at you. And everything that we teach, we try to make sure we have the students just explain the impact of it, understand the impact of it, also understand the importance of data literacy, having diverse role models, lots of different people make AI, and diverse job descriptions doing lots of different things. For the technical curriculum, I thought it would be interesting. So this is all the curriculum we currently offer. I'm constantly making new curriculum. But the Bites of AI are deep dives into specific areas. Explore AI is a broad overview of what AI is, and how it can be used. And you don't have to go through all 30 hours of it, but it's approximately 30 hours. It ends with, remember, you interview your community, you figure out what your community knows about AI, what maybe misconceptions they have, and how you can help solve those misconceptions. And final project about how AI could affect you. We also sentiment analysis and NLP describes NLP, but then explains, like, lets you build things as a program in these areas. And then we're going to mostly focus on the how it works curriculum today, like I said. How it works explains how neural networks work, how RNNs and transformers. So RNNs and transformers are usually used for one words following another. Any time you're using text, it's probably using an RNN or a transformer some way. CNNs are usually what is used to find, like, this is what's in this image, facial recognition, that sort of thing. And GANs are like Wombo art that I gave you the option to play with. Anything that builds something is probably a GAN. So we describe how each of these work. It does not require any programming to do this. And the amount of math that we go into is extremely minimal. So I'm just going to hop around a bit. So for instance, for how CNNs work, it's important to, like, know what a pixel is. And we start out just by having students explore, in case they have not seen a pixel, and understand what a pixel means. They look at this picture. They can see as they zoom in that this picture is made up of lots of squares. And those squares have RGB values. We then also have an activity that allows the students to explore, like, what if you just take the R value? What if you take the G value? What if you take 2, right? So that they get a sort of basic understanding of that. The next thing they consider is, so convolutional neural networks look at pieces. They don't actually look at the pieces out of order, and it would be a problem if they did. But I wanted to show that, like, looking just at pieces of things, you can tell what this is a picture of. Can anyone tell me what is this a picture of? You can put it in the chat. It's a cat. How do we know it's a cat? It's very jumbled. Yep. You can see the eyes. So what we can then tell a student, you can also see, like, I think the whiskers probably help too. You can tell a student that looking at just pieces of a picture, the convolutional neural network can find patterns that are recognizable, like the eyes in this picture were recognizable to you all. Well, how do they find these patterns? I didn't learn about matrices. I maybe learned about it as a junior in high school, but mostly played with them as a college student. So I don't expect them to know what matrices are. Give you a quick intro in the vocabulary. Computers are finding these patterns through filters, which are also called kernels. And these filters are matrices. So a matrix is just a group of numbers organized in columns and rows. Here are some examples of matrices. You can do math to matrices. You can do multiplication. You can do addition. You don't need to know how to do it. The convolutional neural networks do know how to do matrix math. And they do matrix math to change pictures. So I am going to have us go to this site for a moment. Here is a site. You can see kind of again through as you go down here, each of these like squares of 9 pixels is being turned into a square of 1 pixel by applying this matrix. But what I really want you to look at are these kernels here. So if you scroll down to here, you can see blur. Okay, so this picture looks blurrier than the picture looked before. And what's happening is there's these numbers in the matrix to get the picture to blur. What do you notice about these numbers, by the way? Anything that is, let's say, difference between this blur and let's look at the exact opposite of that, which is sharpen. Do you know something about the blur numbers? And the things that I notice is all of these blur numbers are less than 1, as opposed to these sharpen numbers, which are all less than 1 but positive, as opposed to these sharpen numbers where you have like this very strong positive number and we're putting negative numbers around it. So we are bringing out different things. You can also show, for instance, let's say I want to find circles. Or maybe you can see what putting these different filters on the image does. And you can have the students play with them, come up with different filters, and see what happens to the image every time. And then you can have the students share any interesting filters they found. And again, this is to help the students understand this is what's going on in a convolutional neural network. What is going on in a convolutional neural network is matrices, which are just numbers in columns and rows, are being applied to the picture to look at sections of the picture at a time, and to find these sorts of patterns you can find through these filters. So decently high-level understanding of what is going on in a convolutional neural network, but it doesn't necessarily require that you have explained the algorithm itself. It doesn't necessarily require that the students have created a Python program. It just sort of helps them see what is going on under the hood. Any questions about that first? Yeah, blurs have low decimal numbers. Sorry, I was out of the chat for a minute. And a strong number in the middle and negatives. There's a question in the chat, what does each row represent? it's not necessarily the case that it represents any given thing. It turns out people have figured out different matrices that will make different things happen. So that knew that those set of numbers was going to blur it, this set of numbers was going to sharpen it, right? So people have figured some of these out. The convolutional neural network is just kind of figuring things out. It's just sort of building some matrices, figuring out, does this seem to get me the sorts of results that I'm looking for? If yes, maybe I should weight these numbers higher. So it's not that it necessarily, nope. It's just, let me go back to that site. And this is an activity from after students have explored a video and such. But it's just, you can see that like, you look at sort of several pixels at once and turn them into a given kind of pixel based on the math that you're doing to it. So it's not that like, these are not layers of a neural network. This is just each sort of neuron in a neural network, in a convolutional neural network, is doing this thing. There's some really cool visualizations that will show you the neural network itself. I have used them, but I don't have them in this particular slide deck. So if we have time at the end, I'll find it for you. So I give you an example of kind of how high level we go. Another example, so I've mentioned that machine learning in AI, machines are making predictions and decisions. So what does it mean that like it's making predictions? Here is an image of peak breakup times on Facebook. This image is from, I believe, 2008. So you can also talk to your students about how this chart might look different. In 2008, basically everyone on Facebook was a college student. That is very much not the case. I'm not sure I know college students who are on Facebook at all anymore. So looking at, actually, this is the wrong. Looking at this image, let's suppose an AI4ALL student 100 miles away who you've never met, you know nothing about their relationship, asks how likely it is that their significant other is going to break up with them. And the only data you have on breakups is this data. Let's say it's December 25th. What do you say to this person? Do you think they're going to be broken up with? Why or why not? Yeah, on Christmas, December 25th. What makes you think that? Yeah, okay. So if you're using data from like other data that you know, like you maybe have thoughts about your own experience in terms of when people tend to break up, what they're afraid of. But if all you have is this chart, because a machine is only given the data that it was given. It's not given, it doesn't know anything else about the world. It doesn't have its own life experience. And the only data we've given this machine is this breakup times data. Yeah, so Brian's suggesting if it's already Christmas, you should be safe. Why? What makes you say that? Uh-huh. So if we look at this past data, There's a huge peak 2 weeks before the winter holidays, which is maybe people not wanting to deal with the family and such. But on actual Christmas, there's this deep valley. Very few people are getting broken up on Christmas. Do we know that we're definitely correct? Can we say, yeah, no, there's no way you're getting broken up with on Christmas? Nope, not at all. Yep. So what we know is that it's less likely that you're going to get broken up with on Christmas from this data. But A, this number is not 0. There's not no breakups on Christmas. And B, even if there had been no breakups ever on Christmas before in the entire history of Facebook, you still might be the first. So the best that we can do is say, based on the only data we've been given, it looks like on Christmas you are unlikely to be broken up with. And that's sort of how machine learning thinks about things. It has past data. It has it can make predictions based on that past data, but it can't say for sure anything. And I think this is an important thing for students to understand about the kinds of predictions that these machine learning models are making. So we've already also kind of talked about, like, 2 weeks before, actually, you can say, yeah, no, you're pretty likely to be broken up with. And even then, we can't be sure, of course. Maybe they have a great relationship. Other things you can talk about, like I said, this chart comes from 2008. Facebook at the time was almost entirely college students. Facebook now is almost entirely 30-year-olds who were college students when Facebook. You know, those numbers might be different. Maybe more people break up 2 weeks before Christmas while they're still in college next to the other people they're in college with, and they want to break up before Christmas break. Or, like, there's this thing about spring break here, right? So you can also use this to say that, like, who your demographics are going to change the kinds of predictions you make. What your inputs are going to change the kind of inputs you make, that sort of deal. We can also talk about the math behind those predictions. I know this is mostly about how you don't need math, but I do think that this lesson is really well done. So in this lesson, you rate courses. Like 5 is I was super very interested in it, or 7 is I was super very interested in it. 1 was I hated it. So let's say, like, I was super very interested in computer science and I hated math, and I liked but not as much as computer science art or something. And then on a 4.0 scale, I got an A in CS, and I got a B in math, and I don't know, a C in art. Let's say 7. A. Social studies and science. So the idea is this would be your actual numbers, so that you can use your own numbers to understand how these predictions are made. So you graph it, you make the line, and then, like I said, this one does explain the math. But let's say I was really interested in this thing. What grade do I think it would give me? And you can also see that there might be lots of other important aspects here. You might, it might not just be how interested you are. It might be the time of day that decides your grade. It might be whether or not you had friends in the class, right? And so you can figure out what things are actually affecting your grades. And when you are making a prediction about what kind of grade you're going to get, you can find different weights for how important it is for any given interest thing. So this is the mathy part of this lesson. This ends at 12:30, I believe. I think I have till 12:30. So any questions about sort of any of that? All of these slides are taken from varying lessons throughout open learning. Usually, mostly these are how it works lessons, but if you don't have any questions, keep moving on. How neural networks work, I kind of want us to go through the activity if we can get through it, which I think sort of 15 minutes is enough time for that. So the neural network activity has students, first you just get the definitions of the words. We're going to go over these definitions several times in several different ways. But in case you want to go back to the slide that just has the definitions, you can write it down. All of our lessons have handwritten worksheets for the students to work on. And they also all have glossaries. So you can write down the words and their definitions if you'd like. This video mostly explains that it's hard to program a computer to recognize a handwritten digit because different people write numbers very differently. And then this section of video, I'm going to show us. Will people be able to hear if I share? Nope, sorry. Window. That one. Share. I'm going to see. And if you can't hear the video, that's fine. We'll go over it.
As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number.
All right, so based on that video, what is a neuron? He says basically a number. And there's going to be input and output layers.
So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit.
Cool. So in fact, the numbers, what are the numbers in the input layer and what are these numbers in the output layer? Yeah, so the numbers are all going to be between 0 and 1. What are they representing in the input layer? Does anyone remember what a pixel is? Yeah, okay, that's totally fine. That is why there is this question. What are you saying?
So all of these 784 neurons make up the first layer of our network. Now jumping over to the...
So all of those 784 neurons, each neuron was made up of the pixels the numbers from the pixels in the number itself. And then the output, what is it outputting in this case? It's not always outputting this thing, but. Right. So the output for this neuron is 784. How about the output layer? What are the last layer of neurons saying?
So all neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit.
So what is the last layer of this network looking for? Yep. How much it corresponds with the digit. So how likely it is that we're looking at a number 1, how likely it is that we're looking at a number 2. And then in between the input layer and the output layer, there are a bunch of hidden layers. So let's look at those for a minute.
There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with the specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire.
So in much shorter terms than this person, could someone rephrase for me, like, what is it saying? What is it? What happens when one, how do the layers connect to each other? How does one layer make another layer work? Each layer is dependent on the previous one. Whatever happens in one layer figures sort of defines what will happen in the next layer. And then this is sort of more on that. I'm just going to also show us this.
Now, the network I'm showing here has already been trained to recognize digits. And let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents.
And then he describes in this one what each layer is doing. So let's look at that.
And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. that anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the...
So that was a long sort of stretch of video. What is each layer in this neural network doing? Chunking. Chunking is a good, yep. I like that as a single word. They're evaluating the input in smaller chunks. So what I then have students do, I've got to go to this Jamboard. You should be able to edit. Now, to edit this Jamboard, we're going to use sticky notes. And we're going to behave like a neural network that we have just described earlier. So let's say I think 1A should be lit up. I will type 1A, and then I will put it over this 1A here. If you're in person, you can have this projected on your board, but this would mean 1A has lit up. So what I am going to do, let's see. So I know Stacy and Brian are here because they're talking to me, and have recently. If someone else could also volunteer. What I usually do is, what I usually do is split up the class into each set of a couple of people are going to look at a specific layer. So starting with hidden layer 1. This is going to seem less magical this way. It's pretty magical when you don't see it. But this is what hidden layer 1 looks like. So what I usually do is I give people in hidden layer 1 in secret a number. And I have, let's say that number is 9. Okay. And then I have the students who are in hidden layer 1 who know that the number is 9 figure out whether or not they think 9 has a top left corner of a top circle in it. And if it does, I think it does, they light up neuron 1A. And we can keep going from there. You all can pretend we're doing hidden layer 1 together. You should be able to edit this. So do we have a top right corner of a top circle as well? Yep. I'm going to also get us started on hidden layer 2 while people are working on hidden layer 1. So imagine that we have not seen hidden layer 1. All we are seeing are which neurons are lighting up. I have also just given you hidden layer 2. So you'll notice that hidden layer 2 lights up based on the neurons before it. So 2A will light up if 1A, 1B, 1C, and 1D have lit up. So if we go back to our Jamboard, 1A, 1B, and 1C have all lit up. So let's say I think that that is enough for 2A to also light up. And looking at hidden layer 2, is there anything else in hidden layer 2 that should be lighting up now? Do we have like 1E, 1F, 1G? Nope, definitely not that. Do we have 1A and 1B? We do. It's a strict subset of 2A though, so etc. So do we have 1I and 1J? Or we do not. Do we have 1K and 1L? We do. And now that we have started to light up level 2, let's go for the output layer. The output layer looks a lot like the previous layer. So we're looking for ands. Sometimes there's ors. We do have a 2A and a 2G. So given we have 2A and 2G, we have a 2C and a 2L. We have a 2C, but we don't have a 2L, so probably not 0. Do we have a 2G and a 2F? We have a 2G, but we don't have a 2F. 2C and 2I and 2H. We have 2C, but not those, right? So if you go down this list, what number does it look like we're getting? Yep. I'm going to just put this 9 over here. So then you can kind of see that is how a neural network works. We watched it in the video. We described it that way, but now we've also had a chance to play with it. And you can talk to students about how to refine this. You can have students switch off which layers they're playing, just to get a sort of idea of, for instance, we also lit up 2C. Is that a problem? And we can sort of train the neural network and improve it. But that's how neural networks work, and trying to make it more real feeling to the students. And that is most of what I came here to describe. If you are interested in engaging with us further, one, you can always email me. I am Sarah at AI4ALL.org. But also, if you go to bit.ly/open learning teachers, you'll get to this site. Most of our curriculum is available here. We are revamping this website and also the website we're actually using. So if you click this join the teacher community, it will take you to a teacher community that is going to stop existing on July 15th. That is where the teacher community is where all of this locked curricula currently lives. But don't worry, all curricula will be here in fairly short order. And in the intervening time, if you want any of it, you can just email me, or you can email open learning at ai-4-all.org. If you're interested in like some sort of more information, mostly like some sort of advertising materials, if you'd like to start something, and yeah, whoops, our emails are always available here. In fact, the how it works curricula that I was mostly going through is mostly not available on this site yet. But I can share the link to you if you would like. Just email me and let me know. Thank you very much. Just put the link to how it works. It's just a Google Drive folder, so it's currently in Google Drive folder form. But that's how it works. Yes, I play the cello. Not nearly as often as I would like, but I have a friend downstairs who plays the violin, and then and also viola, and another friend who also switches between violin and viola. So every now and again, we get together and play string quartets. Notably, that was only 3 people, but we play string quartets minus 1 part anyway. I started learning cello in about 3rd grade. I love it. Glad it was interesting. I love my job. I love that I get to figure out, like, spend all day watching videos about AI and how it works and understand how it works, and then try to break it down even further than the videos did and give it multiple ways and make it make sense to people. I'm very lucky that way.
Well, I enjoyed it. I think I learned a lot. I was talking to somebody about how impactful AI is and will be, and and the different resources that we have available. And there's more comprehensive resources available than what you would imagine. Like what you shown on your site, it's more than what we would expect. As far as there's a lot of stuff available for you to teach in your classroom and to share with your students.
Yeah, it's also so in addition to the slides, we for each of them offer a teaching guide. So there's a quick overview, and then sort of every single slide will tell you, like, these are the sorts of things students might say. This is the sort of place we're trying to get them to. And if you feel you need anything else, please let me know. I'm always excited to help make things more helpful and to hear how things are going for you.
Will do. Well, we appreciate you, Sarah. It's a very strong session. We're par for the course now. Batavia liked it. Stacy liked it. Yeah, I think we all got a lot from this. Thank you.
Cool. Thank you very much.
I look forward to working with you some more in the future. You will hear some calls or some emails from us. So
awesome. Should I head off, or I can hang around for a bit?
Sure. The next thing we have is like networking and lunch. So feel free to hang out and chat with folks or jump onto the networking and all of that. The next time we'll be on stage is 1:05 for another one of the drawings. for another prize drawing. But everybody, feel free to touch base with each other and hang out. And I'll see you guys again very soon.
Cool. See you.
Peace.
Glad it was helpful. Yeah, this was way more technical than the bites usually go. The bites are usually like input affects output. Here's some inputs, here's some outputs. But I figured this was mostly a conference of people who are already starting to teach CS. So if you're in a CS class, then the more technical things might be useful. I really love the bites, though. They're my favorite things to work on. Also, how it works. I like my job. Did I mention that? Cool. Yeah. If you have any questions, or if you see anything with a block on it on the website and you want access to that, let me know.